So previously we had discussed about several topics like what is the irrigation requirement and how do we determine the various irrigation requirements. We have also understood the methods and also the types of irrigation. Now we would like to go in detail and look at the calculation part of finding out the requirement of irrigation water. So to do that, first we need to understand a few of the topics like duty, delta and base period. First let us look into what is duty, delta and base period. Then we could be able to understand how much is the water required for irrigation supply. Okay. First, duty. So what is a duty is basically duty is explaining you how many hectares of land can be irrigated by supplying 1 cubic of water. Suppose if agency supplies 1 cubic of water, the total land that can be irrigated by that 1 cubic of water is called as duty. Okay, right. Now going to what is delta. Delta is the depth of water that will be applied for any given plant from the sowing to its harvesting period. Okay, so what we do is we supply water in terms of volume, we give in terms of discharge, but if that volume of water is applied on the irrigation field and the depth of water that will be stored on that irrigation field, if it is cumulated from sowing till the harvesting period, that will be called as a delta. Okay, so in general what you have to remember is delta is the depth of water that can be applied to a plant. It's a cumulative depth of water, okay, that will be applied to a plant for the entire growth period of the plant or a crop. Okay, so now duty and delta is very much clear. And base period, going to base period. Base period is basically the total time or the duration from sowing to the harvesting period, means the entire duration where the crop will require water. So that duration is called as base period. So by understanding these terms like duty, delta and base period, where duty is the total area that can be irrigated by supply of 1 cubic of water, delta is the total depth of water that is required for growing of a crop, and base period is the duration of that crop growth. Okay, so by understanding these three terminologies, what we'll do is we'll try to create a relationship between them. Okay, so first let us try to understand what is the relationship that is existing between duty, delta and base period. Now imagine I am supplying 1 cubic of water continuously for a period of b days. As you can see here, base period is represented by b, delta is represented by delta symbol, and duty is represented by capital D. Okay, so suppose if I am supplying 1 cubic of water continuously for a base period of b days. Okay, so the total volume of water that will be supplied for any irrigation field will be this much. Like see, b is the number of days, so 24 hours is multiplied now 60 minutes 60 seconds, so this will give you the number of seconds the water has been supplied. Okay, now how much water we are supplying? We are supplying 1 cubic. Let me explain what is 1 cubic means. Cubic means meter cube per second. Okay, now I want to calculate how much is the volume that is being supplied if I supply 1 cubic of water for b days. So b is the number of days, days multiplied by hours, hours multiplied by minutes, seconds. It will give you the total seconds of water being supplied, and every second we are supplying 1 cubic. So this will give you the total volume of water that is supplied for b days. Okay, now once we understood, next we'll go to amount of water required to flood 1 acre of land with a depth of delta meter. Now if I consider 1 hectare of land is available for me, and if I apply a depth of delta, what is delta? Basically, you remember what is delta is. Delta is the total depth of water that is applied for the entire growth period of a crop. Okay, so what is hectare? Hectare can be converted in terms of meter square by multiplying 10 raised to 4. So 1 into 10 raised to 4 is the area in meter square multiplied by delta, which is in terms of meter. So again this is also a volume. Okay, now let us go to a next slide. Okay, so this is how we establish the relationship. Hence the area in hectare that can be irrigated by 1 meter cube per second running for the base period b days. So what is duty? duty is basically supplying water to any irrigation field. Okay, so B into 24 into 60 into 60, so divided by hectares, 10 raised to 4, this will give you how much is this. Okay, so if you want to find out duty, duty is equals to 8.64 B divided by delta. So duty is equals to 8.64 B, which is base period, multiplied by B. 8.64 multiplied by base period divided by delta will give you the duty. So this is what the relationship that is existing between duty, delta and base period. Okay, now once we have understood what is duty is, and we also have understood how to determine the duty. Duty can be determined based on the delta. Delta is basically the depth of water that we apply for any given crop. So the delta or the requirement changes from one crop to the other crop, and also the base period of the crop changes from one crop to the other crop. So based on that we can calculate the duty for any given crop. Okay, so we will try to understand what are the methods to improve this duty. Okay, now try to observe what all terms that are included in this calculation of duty. So we need to understand base period, and then we need to understand what is delta. So we already know what is delta. Delta is basically the water requirement that is being applied. Okay, so right, now here we will see what are the factors. So if the factors affecting duty may be made less effective, duty of water may be improved. Thus, methods of improving duty are as following. Okay, so first of all, there are some of the points which are written here. Before I go on applying the duty, these factors or methods which are going to improve the duty, let us try to understand what is the process in which the water is being supplied to your field. Okay, now first what we do is we store the water in the reservoir. So there can be evaporation losses, there can be a seepage losses within the body of the dam itself, right? So those are the losses that are going to take place. Now when the water is being supplied through canals, the water carried in the canal may also get evaporated or may get seeped out. Okay, so there is the seepage losses while conveying the water and also while storing in the reservoir. Okay, right. So after water being supplied, what is the next step? The next step is that the farmer utilizes that water to apply to the field, but the method that he adopts to apply water is going to tell you what should be the necessity of water. Okay, if he goes for the more conventional method of application of water, the requirement may increase. If he goes for more modern techniques like sprinkler or drip irrigation, the requirement of water will reduce. Okay, so other than this, I have already explained there are climatic factors, like if there is proper rainfall, optimum amount of water will be stored in the root zone. Because of that, less amount of water can be applied from irrigation. Okay, so other than that, what type of soil is there, what type of crop that we are growing, whether the crop that is grown is only for 2 months, 4 months, or it is grown for an entire year. These are all the factors that are going to depend on the irrigation requirement, right? So here duty is nothing but a system or a method of explaining how much water is required. Okay, so duty is the area that can be irrigated by supplying 1 cubic of water. So you try to understand, if duty has to increase, all these losses has to be reduced. If the losses increases, the duty will reduce. Like for example, if I supply 1 cubic of water, there is a farmer who is irrigating 40 hectares of land, but there is another farmer who is irrigating only 20 hectares of land. Why there is so much difference? Because of irrigation practices. The farmer who is irrigating 40 hectares might be using the most modern techniques so that the losses are very less. So when the losses are reduced, he can irrigate more land. Okay, now going to the other person who is irrigating only 20 hectares of land, try to imagine what he is doing. He is using the more conventional practices. Because of that, the losses will increase. So because of that, he is not able to irrigate more areas. Okay, so this is what we need to understand. So the same thing has been given here, has been listed here. So improving duty means what? less amount of water is used or optimum amount of water is used to irrigate more land. Okay, so what is degradation of duty means how the duty reduces if I use more water and less land being irrigated. So that we call degradation of our duty or reduction in our duty. So this is what we need to understand, and we need to go for methods of improving it. Okay, so what are the methods of improving it? Like I'll just try to basically explain, read out what are the statements that are given here. Suitable and efficient method of applying, I have already explained. The farmers have to use more suitable and efficient methods of applying. Then the canals are to be lined in order to reduce the seepage, and idle length of canal should be reduced. Means the water should be continuously flowing in a canal. And construction parallel canals run side by side. FSL is reduced to minimum the losses, and proper plowing and leveled crop land improves the duty. The source of supply should provide good quality of water. So if it is bad quality of water, it will contain a lot of salt. Because of that, salination will take place. Again, further it may increase the requirement of water. Crop rotations have to be taken place. So these are the same things which I had explained earlier. Okay, so these are the methods of improving our duty. Okay, now let us try to understand what is the relationship between soil, water and plant. Okay, so I have already explained what is permanent wilting point, and I also explained what is field capacity, and I have explained what is saturation capacity. I don't have to explain it again because in the previous video I had already explained it, but just I'll read the statement. Saturation capacity means what? It's the total water content in any given soil structure. Okay, in your geotechnical engineering you have already studied three-phase diagram. What is three-phase diagram is? What you do is that for your engineering understanding, you separate out soil, only soil content. You divide into three parts. Like first what you do is that you divide into two parts. One is soil condition, and then the other one is of your void condition. Okay, so if you can see here, this is your total voids we have. The same phase diagram I am using here. This is the total voids I have, and this is the soil solids that I have. So in these voids, either it can be filled with air or it can be filled with water. Okay, so if this void is completely filled with water, we call it as saturation. If it is less than the saturation level, if there is air available in that void, we'll call it as bulk condition, right? That's what your three-phase diagram explains. So here also the same thing is been applied. If the water is fully filled in all the voids, we'll call it as saturation capacity. If it reduces because of the gravitation, once you saturate the soil, because of the gravitational force, the water will go away and there will be some air that will be left over in the voids. So that part we call it as field capacity. Okay, so the water that is exactly on the field capacity will not be seeped because of gravitational forces. Okay, now if the water level goes beyond the PWP, permanent wilting point level over here, this water, as I explained in the previous video, that it is the water that is stuck to the soil surfaces. So it is called as hygroscopic water, which cannot be utilizable, right? So within this boundary, that is from field capacity to PWP is the water that will be useful for us. Okay, and these are some of the description which have been given. Now the point is, what we do is that when we want to apply water to any field, we want to determine what is the depth of water to be applied. Okay, what is the depth of water to be applied? We are trying to determine the irrigation requirement of a field in terms of depth. Okay, though we supply the water in terms of discharge, we are first determining what is the water required in terms of depth, and depth is multiplied with the area of land to be irrigated. That will give us the volume of water. Okay, now so like for example, optimum moisture content means what? Below, if the water level goes below the optimum moisture content, it is less utilizable by the water. Okay, the plants or the crops will find it difficult to get the water if it goes below the optimum moisture content. So what a farmer does is that he wants to maintain the water level from optimum moisture content to field capacity. If he applies beyond field capacity, it will be seeped out because of the gravitational force. If he applies less than the optimum moisture content, the plant growth may reduce, right? So he wants to maintain the water level between OMC and field capacity, where OMC, as it is given here, optimum moisture content and field capacity. So this is the readily available water. Okay, the level of water between the field capacity and OMC is called as readily available water. Okay, right. So now we'll try to understand how to calculate the depth of water for any given crop. Okay, right. So first let us try to understand some of the terminologies. So let us say dm, or we can call it as small d, as the depth of root zone, total depth of root zone. So you can try to imagine that that's the depth of any given root zone of a crop. Like for example, if you take groundnut, if you take any crop you imagine, there is a depth of root zone for every crop. Okay, so based on that crop, the depth of root zone is determined. So that is the depth with which your roots will go, the maximum depth the roots of that plant may grow. Okay, now we already know what is specific weight of dry soil, which is called as gamma d. We know the unit weight in terms of saturation, bulk density and dry density. So this is what it is. So specific weight, or you call it as unit weight in your geotechnical engineering. So specific weight of dry soil, we call it as gamma d. And let us take a cross sectional area. Okay, let us take a small patch of area, which is the cross sectional area of the soil will be considered as A. Okay, and the depth of water present in the voids, we'll call it as D, capital D. Okay, so if you want to calculate how much is field capacity, I'll call it as water content itself. So how do you determine the water content in your lab? Weight of water retained in certain volume of soil. It means the weight of water divided by weight of volume of dry soil. Okay, so what you do, the same experiment you do in your laboratory also. First what you take the weight of the soil sample when it is filled with moisture. Then you put that soil into the oven, and you take once it is completely dried, you take out that soil and you weigh it, and you determine how much is the weight. So from that you calculate how much is the weight of water, and weight of water divided by weight of soil will give you what is the water content, right? So here water content is nothing but your field capacity itself, right? What is the percentage of water that we have? So let us write what is weight of water retained in certain volume of soil. So area multiplied by depth of water multiplied by unit weight of water, which is gamma W. So this completes your weight of water retained in certain volume of soil, divided by weight of soil. So how to calculate the weight of soil? Area multiplied by depth of root zone, which will give you the volume of soil, multiplied by gamma D. Gamma D is your unit weight or specific weight of dry soil. So this completes your numerator and denominator. Okay, now as we know, area will get cancelled. So we are interested to determine what is the depth of water, right? We can just send these terms to right hand side, and this is what the equation that will get developed. Gamma D divided by gamma W. What is gamma D? Gamma D is the unit weight of dry soil. Gamma W is the unit weight of water. So gamma D by gamma W is nothing but the specific gravity of the soil itself. I hope you all remember it. Okay, so what is D? D is the depth of root zone. What is FC? FC is the field capacity. Okay, now if you want to determine how much is the depth of water that is available in the soil, we can use this equation, where this equation is S, specific gravity of the soil, multiplied by depth of root zone multiplied by field capacity will give you what is the depth of water available, right? Now similarly, if I want to determine how much is the water between PWP to FC, okay, so the depth of water, what we do is that we use a specific gravity multiplied by depth of root zone multiplied by FC minus PWP. So FC and PWP are two water contents. Okay, FC is the maximum water content, that which is called as field capacity. PWP is the lowest level of water content which cannot be useful for the plant, right? So like this, a different depth of water that can be determined. Like for example, if I go to earlier figure, in this figure you can see, if I want to determine how much is the depth of water required for hygroscopic water, what I do is that I'll multiply specific gravity of this soil multiplied by the depth of root zone multiplied by this water content. PWP will give me what is the depth of this water. Okay, now similarly, if I want to find out what is the depth of water till field capacity, what should I do? I should multiply specific gravity multiplied by depth of root zone multiplied by field capacity will give you what is the level of water. Okay, so this is how we can calculate the different depths of waters. Okay, right. Now coming to what is consumptive use. Consumptive use is the term that is already being used, I guess, while explaining what is evapotranspiration. So here consumptive use of is defined as with the perspective of a farmer. If you are an engineer, you would call it as evapotranspiration. If you are a farmer, you are calling it as consumptive use. For engineer, it is a loss, evapotranspiration. It is getting evaporated and it is getting by the method of transpiration, the water is getting into the atmosphere that is available on the surface. Here the farmers look it as a consumptive use. He is consuming that water so that he can grow the crop, right? So in more or less the terms are same, but their usage is different. Like for example, if an engineer uses it, he may use it for a forest land also, he may use it for a barren land also, he may use it anywhere. But when it comes to consumptive use, this term is used only for from the farmer side itself, because he is consuming that water to grow that particular type of crop, right? So consumptive use is specific to the agricultural field, but evapotranspiration is a term which can be used universally anywhere to any plant, which may not be useful for the livelihood of humans. Okay, right. Now the same thing, what are the factors that are affecting your consumptive use? First thing is evaporation. Evaporation is basically dependent on temperature. Then how much is the precipitation that is taking place? If there is more precipitation or there is a uniform supply of water from the rainfall, he will use less water from the irrigation, so that's why the consumptive use will reduce, because basically we are applying the artificial water, right? Now the wind velocity, as we know already, if there are some of the factors that are similar to the factors that are affecting in the evapotranspiration also. While you are studying evapotranspiration in the second module, they might have discussed about the factors that are affecting the evapotranspiration. So these are the same factors that are influencing in case of consumptive use also. Type of soil and topography. So depending upon the type of soil, whether it is pervious or impervious, based on that also the consumptive use may increase or decrease based on the topography. If the terrain is flat, less amount of water will convert into runoff, and if it is slopy land or if it is a mountainous terrain, more water will flow because of the gravitation. Okay, now cropping pattern. What is your cropping pattern? What is the growth stage and what is the type of crop? Like see how in what pattern do you apply your crops, and then what is the growth stage? Initially the requirement will be less. When it is in a matured condition, the water requirement will reduce. Again, when you are going towards the harvesting, the water requirement will reduce. Like this on the basis of type of crop it is. Okay, the water required for a paddy field is different compared to the water required for sugarcane field or groundnut field or wheat or anything like that. So growing season, in what season that you are growing, that is also going to depend on consumptive use. Then the other things that will be applied only for consumptive use, the factors that are going to affect only consumptive use is method of irrigation, or the method of applying water to your fields, whether you are going for more conventional method or more modern techniques. Okay, then the irrigation, water depth and daily light hours. So these are the list of your